Good afternoon, class. This is the spring semester of 2020. We're at College of the Sequoias in the Central Valley of California. And in this section, we're going to look at partial fractions and their decomposition. So this is 9.4. I did 9.5 before 9.1 because it's nonlinear equations versus linear equations. 9.4 changes it up. We're looking at partial fraction decomposition. We're not going to do 9.2 and 9.3. Those are linear algebra topics, and you will learn about them in linear algebra. So let's focus on stuff that's important that you have for calculus. So partial fraction decomposition is sort of like this. What happens when we add two equations or two rational expressions? When we end up doing it, if you work this out, and we did this in a previous section, we would end up with x times x plus 1 on the bottom, 5x plus 5 times x plus 3 on top. Here we added rational expressions. Going from left to right, we added the expressions. Going the other direction is called partial fraction decomposition. So there's a way to tear these fractions apart. This is why do you ask? This is extremely useful when you start integrating in Calculus 1 or 2, depending on what school you attend. I'm assuming you attend our school, College of the Sequoias, but this may end up spreading beyond our school. So this is extremely useful when you begin calculus and you start integrating. Start integration techniques. It is a lot easier to integrate what's on the left than it is on the right. So let's talk about some general rules, or the general approach, and how we're going to look at it. I don't even think we're going to be using Desmos. So we start off with a rational expression where we have some function of x on top, and on bottom we have a function g of x. So steps. If f of x has a higher degree than g of x, it's an improper fraction. And we're going to start off by dividing the denominator into the numerator. Numerator. Into the numerator. If you're lucky, if you can get it to work, synthetic division works. You might just have to do good old polynomial division. An example of this would be, and we're not going to work it out, and we're not even going to really use this one. If we had this over this, if you ended up doing the division, Now the remainder has a degree where the numerator is smaller than the denominator. So step 2, that's only if it's improper. This step is often unnecessary. Frequently for what you use it for, as g of x is usually of higher degree. Not, well, I don't want to say usually, is often of higher degree. So after this, this is where it really starts. Step 2. Factor g of x, the denominator, completely into the forms, into factor forms of, we can have ax plus b up to some power. We could even have a quadratic in the denominator. This gets a heck of a lot harder if it's beyond quadratic. We'll assume m and n are positive integers. Or better yet, let's just call them natural numbers, the whole numbers. And these are irreducible. Like you can't factor this any further. Okay. So what we're going to do, and this is a little confusing in words. It comes a lot clearer when we work it out, but I want to illustrate it or write it out. So for every, let's look at each ax plus b term. So step 3. For each distinct linear factor, ax plus b, the decomposition has of a over ax plus b. Then we had this was ax plus b to the m. If m is greater than 1, it decomposes like this. We'll have a1 over ax plus b to the first power plus a2 over ax plus b to the second power plus, if we have an a3, just so you see how the trend is going, all the way up to m terms. Step 4 is similar. We have cx squared plus dx plus e to the n. This decomposes into a bx plus c term over the cx squared plus dx plus e. That's if n equals 1. If n is greater than 1, we will have like b1 x plus c1 over cx squared plus dx plus e to the first power plus b2 x plus c2 over cx squared plus dx plus e the second power, and this goes up to n terms. And after we have that, so we will write the equation, step 5. Make an equation with the full decomposition on one side and f of x over g of x on the other side. And use algebraic techniques to figure out A, B, and C. Now, this becomes a lot clearer when we're doing it. Okay, let's look at some examples. This is a crucial tech skill to learn for calculus, crucial. So we'll start off with 2x to the 4th minus 8x squared plus 5x minus 2 divided by x cubed minus 4x. Right now, the degree on top is bigger than the degree on bottom. So we're going to do long division. Remember, any missing term gets a 0 exponent. And we go until we have a degree in the remainder that's lower than this degree out here. So 2x to the 4th divided by x cubed is 2x. Put the 2x here. This is 2x to the 4th minus 8x squared. Or 8x squared. Ooh, that comes over here. Line it up with the right thing. And then we subtract. And we move the subtract in, it changes all the signs in here. Add vertically, and those both go away. And we end up with 5x minus 2. So this decomposes into that's step 1. Step 2 is we want to factor the bottom completely. So step 2, factor g of x. which equals x cubed minus 4x. The first thing we can do is factor out a greatest common factor, which is x. And this actually simplifies more. That's the difference of squares. So each of these terms only shows up once. I am going to have my original fraction on one side. I'm just going to work on this end part here. So we're going to have 5x minus 2 over x cubed minus 4x. That equals, well, since we have a whole bunch of things like this, rather than using A1 and A2 and A3, I'm going to use A, B, and C. I can have A over the x term plus B over the x minus 2 term plus C over the x plus 2 term. And the algebraic technique we're going to use, clear fractions via multiplication. Multiply by g of x. Times x cubed minus 4x over 1. And I'm going to use the factored form of g of x on each of these. You'll start, once you get some practice with this, you will start skipping this step, because this just takes up a lot of writing, really. Where these two are equal. So all I did is multiply everything by the common denominator. What happens? X cubed minus 4x cancels out of there. I'm going to start this on the next page. So on the left side, I get 5x minus 2. And next I have x's cancel. And I have a times x minus 2 times x plus 2. Here, the x minus 2's cancel. And that's what's left there. And finally, x plus 2's cancel, and we have you want to expand this all out. I'm doing it in steps, just doing the x parts first. There, I just distributed the capital letters inside. Now gather like terms. Which terms have an x squared? I have ax squared, bx squared, cx squared. So I have a plus b plus c times x squared. And then for x, I have 2b and negative 2c. And finally, for no x, I've got minus 4a. I'm going to put in a 0x squared here because it's kind of important that you see where this is coming from. Just making sure I didn't make any mistakes. Everything's looking good. I gathered the right things. Okay. Now on left and right, equate coefficients for like terms. So for the x squared term, I have 0 and a plus b plus c. 0 equals a plus b plus c. For my x term, I have 5 equals 2b minus 2c. And for my constant term, I get negative 2. We've got negative 2 equals negative 4a. So here we set coefficients for like terms equal to each other. Now solve where you can. The bottom one's pretty easy. So I'll put a little box around this. We're going to use this. These are the ones we started with. So negative 2 equals negative 4a. We divide by negative 4. We show that a equals 1/2. So I can plug that in. I get 0 equals 1/2 plus b plus c. Let's move that to the other side. And I get b plus c equals negative 1/2. And the other equation I have is 2b minus 2c equals 5. Now we use stuff from the system of equations. I want to clear these, figure out what these values equal. That one's already determined. So I can multiply this by 2. And if I do that, I get 2b plus 2c equals negative 1. I can add vertically, and I get 4b equals 4. You guys with me there? This tells me b equals 1. And I'll plug that in here. And I get 1 plus c equals -1/2. So c equals -1 minus 1/2 is -3/2. Let's pause for a second, make sure everyone's on the same page. Okay, so we're going to use those. Let's rewrite what we had. We had 5x minus 2 over x cubed minus 4x equaled a over x plus b over, which one did I have? X minus 2 plus c over x plus 2. And now we plug in our values for a. B and C. We have a equals 1/2, b was 1, c was -3/2. So on the ones that have a fraction on top, you can move the denominator down below. One over 2x plus 1 over x minus 2 minus 3 over 2x plus 2. Or plus and a negative on top. So going all the way back, we had 2x to the 4th minus 8x squared plus 5x minus 2 over x cubed minus 4x. That had to equal 2x plus this thing, 1 over 2x plus 1 over x minus 2 plus -3 over x plus 2. That's how partial fraction decomposition works. It's a long process. That one problem took us 3 pages. You start getting used to it though. It's a lot of algebra steps that once you've done it a couple times, the hard thing is remembering what goes on with each equation. What do I put in when there's different terms? So let's take a look at another example. Let's show you one where the denominator has a linear term that repeats. Let's do 2x over x minus 1 cubed. So I told you this had to go a over x minus 1. Then we had a2 over x minus 1 squared plus a3 times x minus 1 cubed. This was our step 3. So when you have a term that's got an exponent that's not 1, this is what you have to do, where the exponent matches the subscript. Techniques for solving are the same. Clear the denominator. Clear fractions. So we multiply by x minus 1 cubed. Nice that it was already factored. That was nice. I'm just rewriting everything, and then I'm going to put in my multiply through by my x minus 1 cubed. and we see what we end up with. So on the first one, the x minus 1 cube's clear, and we get 2x. Here, only one of them goes away, and I'm left with x minus 1 squared. For A2, two of them go away. I'm left with x minus 1. And here, all of them clear. We have A3. And note, you can use A, B, and C rather than A1, A2, A3. I was just using it consistent with the descriptions I gave you. So we're going to expand out what we've got. This is x squared minus 2x plus 1. And we'll distribute. And I've got x squared terms, so I'm going to say 0 x squared plus 2x plus 0 equals a1x squared minus 2a1x plus a1 plus a2x minus a2 plus a3. And now I'm going to group things that have the same term. I've only got one x squared term. My x terms and then my constants So what do we get? Let's line up our x squared terms, our x's, and our constants. I get 0 equals a1. I get 2 equals negative 2a1 plus a2. And I get 0 equals a1 minus a2 plus a3. This tells me right away a1 equals 0. So I'll plug that in there. And I get 2 equals negative 2 times 0 plus a2. So a2 equals 2. And we'll plug that in here. 0 equals 0 minus a2 plus a3. And we solve for a3 and we see that a3 equals 2. And now we're going to plug it back into our composition up here. What does 2x over x minus 1 cubed turn into? The A1 term goes away. A1 was 0, so we don't need the first one. A2 was 2, so I have 2 over x minus 1 squared. And A3 was 2. 2 over x minus 1 cubed. The way it gets easier is we don't have variables or x's on top and bottom. It gets a little easier that way. I want to show you a way that'll speed it up. We're going to do it on the last two problems. I'll do it here, and then I'll do it on the last problem as well. We'll pull it back up. So let me rewrite what we had. We had 2x over x minus 1 cubed equals a1 x minus 1 plus a2 over x minus 1 squared plus a3 times x minus 1 cubed. And when we rewrote it, we had 2x equals a1 x minus 1 squared plus a2 x minus 1 plus a3. Notice I have x minus 1 and x minus 1. What if we plug in x minus 1, or x equals 1? How did I get that? X minus 1 equals 0, solve for x. If I plug that in, I have 2 times 1 equals a1, 1 minus 1 squared, plus a2, 1 minus 1, plus a3. And a1, 1 minus 1 is 0, this goes away. 1 minus 1 is 0, this goes away. This tells me immediately that a3 equals 2. This can fast track it. This idea fast tracks it. Plug in values that make term 0. I'm going to pull up the one we just did a little bit ago. We had 5x minus 2 over x cubed minus 4x equaled a over x plus b over x minus 2 plus c over x plus 2. And when we rewrote that, we had 5x minus 2 equals a times x minus 2, x plus 2, plus bx times x plus 2, plus cx, x minus 2. There are three things that make the bottom 0. X equals 0, x equals 2, x equals negative 2. If I plug in x equals 0, what happens? I get 5 times 0 minus 2 equals a times 0 minus 2, 0 plus 2, plus b times 0 plus 2, plus c times 0 minus 2. A lot of stuff goes away. You get negative 2 equals, this is negative 2, this is positive 2, this is negative 4a. B times 0 is 0, c times 0 is 0. Gone. We immediately get a equals 1/2. What if I plug in x equals 2? 5 times 2 minus 2 equals A times 2 minus 2, 2 plus 2, plus B times 2 plus 2, plus C times 2 minus 2. 5 times 2 is 10. I'm starting to rotate my camera. 5 times 2 is 10. 10 minus 2 is 8. 2 minus 2 is 0, so the A term goes away. The B term is 2 times 4 is 8. And the C term goes away, and we get B equals 1. That goes to 0, and that goes to 0. And if we do x equals negative 2, five times negative 2 minus 2 equals A times negative 2 minus 2, negative 2 plus 2, plus B times negative 2 plus 2, plus C times negative 2 minus 2. This is negative 10 minus 2 is negative 12. Negative 2 plus 2 is 0. So these two terms go away. And I get negative 2 times negative 4 is 8. C equals negative 3/2. Go back and look at what we had before. Those are the three values we had. A equals 1/2. B equals 1. C equals negative 3/2. So this method can speed things up substantially, plugging in the things that zero out terms. It doesn't always work, okay? But usually works pretty well. So let me give you guys another one to try. Let's do this one. Let me give you guys one to try. You guys try. Pause the video and try solving that out. Okay. I'll assume you did. We're going to have A over x minus 3, the first power. I'm going to use B and C because the subscripts can get confusing. And when we multiply through by our x minus 3 cubed, well, what if I plug in x equals 3? We can fast track it a little bit. 3 squared minus 4 times 3 plus 7. That's 9 minus 12 is negative 3 plus 7 is 4. Equals, the A term goes away, the B term goes away, C equals 4. Now I'm going to have to expand it out because there's nothing else I can plug in. That'll zero it out. I can at least put the 4 in. And I can even subtract 4 from both sides. And now we distribute our letters. And I will group like terms on the right. There's only one ax squared, or 1x squared. For x, we have negative 6a plus b times x. And for the constant, we have 9a minus 3b. So now we'll look at our terms. We got x squared, x, and the constant. On the left side, we have 1. On the right side, we have a. For the x term, we've got negative 4 on the left. On the right side, we have negative 6a plus b. And for the constant, we have 3 equals 9a minus 3b. This one gives us a equals 1 pretty clear. Plug it into either one. Negative 4 equals negative 6 times 1 is negative 6 plus b. And we get 2 equals b. You should get the same thing if you plug it in here. And this tells me that x squared minus 4x plus 7 over x minus 3 cubed decomposes into 1 over x minus 3 plus b, which is 2 over x minus 3 squared, plus c, which was 4 over x minus 3 cubed. Okay. Now let's switch to one that has something more to it. So far, we've only had linear terms on bottom. Let's come up with something that's a little bit bigger. Let's decompose now here. The term with the x plus 4 just gets an a on top. When you have a square in the term, you don't just put b, you put bx plus c. We clear fractions. So actually try working that out. Try working it out, see what you get. This is the only thing that's changed, making it a bx plus c. Okay, I'm going to assume you did. When we clear fractions, we got 8x squared plus 10x minus 3 equals a times x squared plus 1 plus bx plus c times x plus 4. Looks like x equals negative 4 is a good one to plug in. Let's give it a try. And this term goes away. So what do we have here? 8 times 16 minus 40 minus 3 equals 16 plus 1, 17a. Ooh, that's ugly, isn't it? Not bad. A equals 5. At least we didn't end up with a crappy fraction to work with. Now let's go and distribute and plug in what we got. I'll put in the a equals 5. I can't really do x squared plus 1. Not very friendly, because I could make that 0, but what do I put in for x? I end up having to put in I or negative I, and it's complex. I'm not really comfortable doing that. I want to see what happens if we just work it out. That's that one. Here we got to distribute. Take your time. My x squared terms are 5 plus b x squared. My x terms are 4b plus c. And my constants are 5 and 4c. So now we'll equate coefficients. We got our x squared, our x, and our constant terms. 8 has to equal 5 plus b. 10 has to equal 4b plus c. And negative 3 has to equal 5 plus 4c. This tells me b equals 3. Subtract 5 and we get 4c equals negative 8. This tells me c equals negative 2. Which you could have gotten by plugging b in here and solving as well. So our fraction decomposes. We had 8x squared plus 10x minus 3 over x plus 4, x squared plus 1. Our a term is 5. B was 3. This was our x squared plus 1 term. B was 3, so we have 3x, and c is negative 2. Okay, let's go for a big one. Yeah, that's not big enough. Let's go crazy. Okay, so first off, we want to decompose that. I need a term with x on bottom, a term with x squared plus 2 on bottom, and a term with x squared plus 2 squared on bottom. I can use a here. I'm going to use bx plus c here. And let's do dx plus e here. go ahead and try to work that out. Pause it. This will take you a good 10, 15 minutes to do, at least, because you don't want to rush it. I'm going to assume you paused it and did so. We clear the fractions. We've got a times x squared plus 2 squared plus bx plus c times x squared plus 2 plus dx plus e times x. Well, x equals 0 will end up clearing out this term and this term. So what happens if we plug in x? Everything over here that has an x goes away. We get 4 equals, and this goes away, this goes away. We have a times 0 squared plus 2 squared, which is 4a. 4 equals 4a tells us that a equals 1. Okay. All right, now the tedious part. I'll put in the a equals 1. I've got x squared plus 2 squared plus this is x to the 4th plus 4x squared plus 4. I'm going to do this in steps. I'm going to move the x in over here. We've got x cubed plus 2x. Here we got dx squared plus ex. Before I go down, I'm going to subtract this over. Which makes the left side a lot smaller. And we'll distribute over here. I've got bx to the 4th plus 2bx squared plus cx cubed plus 2cx plus dx squared plus e. So let's gather like terms on the right. Circle a equals 1. I don't want to lose that. X to the 4th term, I've only got 1. The x squared terms, I've got 2b plus dx squared. And nothing else repeats. Cx cubed plus 2cx plus e. Now we start equating terms. I don't want to put the equal sign in. This is a colon. I got no x to the 4th on the left. This says 0 equals b. Done. That's locked in right away. X cubed. I have a 3 on the left, 3 equals C. Wow, look, that's locked in right away too. X squared, I got 0 equals 2b plus d. My x terms, something's missing. That's an EX. So that's 2C plus E X. Let's get rid of that. So 2 equals 2C plus E. And our constant said 0 equals 0. That's not any helpful. We don't have anything there. Well, B equals 0 and C equals 3 helps. If I plug that in there, I got 0 equals 2 times 0 plus D, which tells me D equals 0. If I plug in 3 there, I get E equals -4. And I can rewrite my deconstruction now. So I start out, I got A equals 1, so I got 1 over X. My B and C are the next ones. I got 0x plus 3, so just plus 3. And my dx, that dx goes away. I've got -4 over x squared plus 2 squared. And that's kind of it in a nutshell. So anything that repeats, any denominator that repeats, like has a higher exponent than 1, you have to make sure you just do more terms with it. If it's got an x squared in it, you got to make sure the numerator has an x and a constant in it. Other than that, all done. That's 9.4. This is an essential skill for calculus. So you should very, very, very much practice this and learn how to do it. All right? Peace. Till I see you next.